pretty sad. I mean, that's the best I've ever drawn anything ever. Yeah, it's great. It's wonderful for me. Um, Nothing else has even come close. So this, yeah, makes a man feel good. So anyway, we're taking this length S. This length S corresponds to this component here. That's arc length. All right. That's the part of the formula from the previous topic. The integral of just that radical. That would give you the arc length forward integral. Right? The rest of it comes from this 2 pi r business. Right? So if I'm finding the surface area, what I'm doing is I'm taking the circumference of each point as it's spun around whatever the axis is. So this is my axis. I'm taking the circumference of each point. Because I only care about the outermost portions. So I need the circumference. All right. And that happens to be 2 pi r. 2 pi times the radius. So if I just have some expression that represents the radius at any point on that interval, so that it's a variable radius. So sometimes it'll be smaller, sometimes it'll be bigger. If I can come up with an expression that represents that radius, then I'll have everything I need in order to find surface area. Okay? And what we get out of this is sometimes that radius is going to be in terms of x, and sometimes it's going to be in terms of y, depending on the orientation of the figure. Orientation of the figure meaning what type of axis is it being revolved around? Is it being revolved around a horizontal axis, in which case your thickness of that radius, the rectangle that goes along with that radius, would be in terms of x? Or is it being revolved the other way, in which case the thickness would be in terms of y? All right? So that's really all there is to it. In the case of each of these functions, it's just really a matter of kind of following the process. Okay? And the process is determined based on what you see in the model itself. Right? So find the surface area formed by revolving the graph of f of x equals x cubed on the interval of 0 to 1 about the x-axis. Just because I don't feel like drawing like ever again, I'm using the calculator to draw for me. This one's easy enough to draw, I just don't want to. I mean, you could even just tell it what the range would be, because you plug into 0, you plug into 1, it's going to be 0 and 1. Or you could use a zoom fit process too. All right, so we're spinning this around the x-axis. All right, so we're going to have a rectangle that has a thickness x. From that, we get a radius. All right, that radius, that r of x, is going to be the distance to the curve itself. All right, the rest of it is just procedural, because I know I'm working on an interval of 0 to 1. I have a 2 pi on the interval of 0 to 1. My r of x is the distance out to the function itself. Right? So that r of x is really a y, but y is x cubed. One plus, we need f prime, which is 3x squared, power rule from Calc 1. And we can just run it through the mill. All right, so break out the old calculator. And really, again, just I'm not looking for appreciation or anything, but these would be a real pain in the you know what if you had to do them by hand, because each one of these integrals that we've been doing involves either u substitution, integration by parts, partial fraction decomposition, trig substitutions. Just basically, most people teach this stuff after they teach. Fun fact, that's a new way of pronouncing words. Taught all that other stuff, so that they can hit you with this and have you get like tons of stuff wrong. Sorry, I put the wrong thing in there. I don't think they're that mean. That's just the way they do it, and that's the way textbooks do it. I don't like to do it that way, because I think the calculator can allow you to demonstrate knowledge of the theory behind the motion without you being bogged down with the actual analytic solution. All right. So yeah, because this would be a nightmare, and it compounds because, like, just imagine I put a question like this on a test in Unit 2. You don't get, like, you did everything right in terms of coming up with a surface area model. The only thing you got wrong was the fact that you had trouble finding an integral, and because of that, like, everything fell apart. I don't want to put you through that. All right. So, solution. So again, I mean, I've said it a bunch of times. Enjoy the calculator while it lasts. It won't be here forever. As long as it is, it should hold a special place in your hearts. All right. Well, here's hoping I made the edits on number 2. Otherwise, it's going to be the exact same problem as number 1, just with a different function. So x squared on the interval to, oh, it already looks different. Okay, good. On the interval of 0 to root 2, calculator converts that over to decimal form. Doesn't matter to us. Zoom fit of y min or max, clear zoom 0. Now that part does look exactly the same, but we do know it's a different function on a different interval. So it should have some slight differences. All right, so we're spinning this around the y-axis. All right. So that means that we're looking for y stuff, changing our perspective. So our arbitrary rectangle dy, that represents our radius. Now that radius is going to be a function in terms of y. All right. One thing you got to be careful about when it comes to this topic is this formula, at least initially, looks an awful lot like cylindrical shells, to the point where if you're going to mess it up, it's because you're probably going to place your rectangle parallel to the axis of revolution, because you see the 2 pi and you automatically associate that with cylindrical shells. This is different. We're back to perpendicular rectangles. All right. The only case where the rectangles are parallel to the axis of revolution is in the case of cylindrical shells. All right. Now, if you have not yet figured out what the bounds would be, that's all right. The calculator figured it out for you. 0 to 2. I mean, it's trying to tell you 2. It's just stuttering a little bit. All right. So 2 pi on the interval of 0 to 2. I need my r of y. So r of y would be this function. So this function, which we know is y equals x squared, but solved for x in terms of y. All right, so this would be the same as saying, if I took the root of both sides, x equals the square root of y. All right. Depending on what axis you're living on, sorry, what side of the axis you're living on, it may be positive or negative. We're above the x-axis, so that means that our y equals x squared should be positive. We're to the right of the y-axis, which means our x equals y, root y should be positive. Okay, so we're in good shape there. So I have my r of y. I also need f prime of x, which is easily enough. Oh, sorry. Yeah. Really wanted that to be a little easier than it would end up being. All right, so let me just make a note down here. This is the same as saying f of y equals root y. Root y is the same as y to the 1/2. So I have to differentiate that. F prime would be 1/2 y to the negative 1/2. All right, so again, I'll come back to that in a second, but that we're going off of this one. All right. So, square root of 1 plus my derivative 1/2 y to the negative 1/2 squared by. All right, so all of that was just us manipulating the information that was given, because it was given as a function in terms of x, so we needed everything to be in terms of y. All right, so a little annoying, but manageable, somewhat. So to the calculator. Math 9. Forgot the 2 pi again. Back arrow. Insert 2 pi. Easier to just hit clear. 0 to 2. I'll put it in with the y's. Root of y alpha 1. The right arrow, parentheses. Oh, actually, it's another root. Nah, I'll put parentheses anyway. Root of 1 plus parentheses, write it as 0.5 y raised to the negative 0.5. So I don't have to bother with fractions, close them up, square it, and y again. All right, so overly convoluted. Maybe I definitely think a little bit of algebra would simplify what you have to put into the calculator, because even just squaring your 1/2 y to the negative 1/2, even just squaring that makes it a little bit nicer. So we're looking at that. And again, the numbers are what the numbers are. You look at them and you say, all right, yeah, cool. 13.6, that's the surface area of this hole or something. I don't know. Yeah, we don't really have much of a sense of scale here, so expect ugly numbers. Actually, be more on guard if you have nice, clean answers. That's what I would say.